Welcome back to Physics 192. I'm Gerard Blanchard. This time we're going to talk about electrical potential energy. Electrical potential energy is very similar to gravitational potential energy in its second form, as we discussed at the very end of Physics 191. At the end of Physics 191, we gave an equation for the gravitational potential energy of a mass, little m, due to the spherical Earth, which will give a mass, capital M, and that gravitational potential energy was U sub g is equal to minus little m times big G, where big G was our gravitational constant, times big M divided by R. That was our universal gravitational potential energy equation. Similarly, the electric potential of a charge Q, little q, due to another charge, which we'll symbolize with big Q, is UE is equal to little q times our constant K times big Q divided by R, where R is the separation of the centers of the charges. So let's apply this equation in an example. How much work is done by an applied force that moves two charges, which each have a charge of 6.5 microcoulombs, that are initially very far apart to a distance of 4.5 centimeters apart? Now for this, you can start with one charge at the origin, say, and leave that charge stationary and just move the other charge. So one charge is stationary, and we're going to bring the other charge in from very far away. We'll call that infinity. So one charge stays still and the other charge moves in from infinity. And how much work is done? This is an energy situation. The word work is a clue that we're talking about energy. And we're going to use our new expression for electric potential energy. So I'll give you a little bit of time to set that up and start working and see if you can stay ahead of me. Okay, here is our stationary charge. I'll call that big Q, and it has a charge of 6.5 microcoulombs, so it'll be 6.5 times 10 to the minus 6 coulombs. And here is our other charge, little q, and it also has a charge of 6.5 microcoulombs, so 6.5 times 10 to the minus 6 coulombs. And it is initially very far away, or infinitely far away from this charge. And we'll say that it is at rest. So V initial is equal to 0. So it's at rest, infinitely far away from this charge. We bring it in to a final distance, R final, of 4.5 centimeters, or 0.045 meters, and we will stop it. V final is equal to 0. Now that information was not explicitly present in the question, but since we were not told anything about the speeds and we were not asked about the speeds, we have to assume that they are 0. Or at least that they don't change, and we'll see why in a second. Okay, so that is everything that we were explicitly given in the question, and and we were asked for what is the work done. So the fact that we're asked for work tells us that this is an energy situation. And in energy situations, our equation always is work non-conservative, the work done by non-conservative forces, is equal to the final kinetic energy minus the initial kinetic energy plus the final potential energy minus the initial potential energy. And since this charge was at rest to begin with, and this charge it's at rest to end with, and this charge is at rest the whole time, kinetic energy final and kinetic energy initial are both 0. Now, we didn't have to assume that these charges were necessarily at rest to begin with and end with, but we would have to assume that at least that the kinetic energy doesn't change, so that kinetic energy final minus kinetic energy initial between the two of themselves would cancel out. And the reason we have to assume that is because otherwise we wouldn't have enough information to answer the question. So in order to answer the question, we had to assume that these were at rest, or at least that their speed did not change, that its speed did not change in a non-negligible amount. Okay. So work non-conservative is equal to potential energy final minus potential energy initial. Since the force between these charges is the electrical force, this would be the electrical potential energy final and the electrical potential energy initial. Or the work done by non-conservative forces. We now have to substitute in for our expression for the electric potential energy, and that would be little q times k times big Q over R, and it would be the final separation between the two charges, minus Q times K times big Q over the initial separation of the charges. And we know Q, we know K, we know big Q, we know R final, we know all of this, so we know everything over here, so we can calculate work non-conservative. So work non-conservative is equal to 6.5 times 10 to the minus 6 times K, which is 8.99 times 10 to the 9, times big Q, which is 6.5 times 10 to the minus 6, divided by R final, which is 0.045, minus, and I'm just going to write Q, K, big Q, divided by R initial, which is infinity. And so regardless of what Q, K, and big Q are, as long as they're finite, any finite number divided by infinity is 0, so we don't have to actually calculate that term. Okay, so it leaves us with work non-conservative is equal to 6.5 times 10 to the minus 6 times 8.99, 6.5 times 10 to the minus 6 times 8.99 times 10 to the 9 times 6.5 times 10 to the minus 6 divided by 0.045, and that gives us 8.44 energy units, so joules. So the work done to bring this charge from infinitely far away from this charge to 4.5 centimeters away from this charge is 8.44 joules. And the reason why we had to do work is that the potential energy of this charge is low when it's very far away from this charge, and it gets higher as it gets closer. So its potential energy has increased, its kinetic energy hasn't changed. So something must have given energy to this charge to bring it in, and that is the work done. And specifically, it took 8.44 joules of work to bring this charge from here to here. Let's work another example. This time we have multiple charges, as you can see in the diagram. And the question is, how much work does it take for an external force to set up the arrangement of charged objects in the diagram on the corners of a right triangle when the three objects are initially very far away from each other? Now, the way that we'll work this is that we'll assume that one of the charges, we'll say the negative 6.5 microcoulomb charge, we'll put that at the origin, and we'll say that that charge was in its position initially and it doesn't move. And then we'll bring in one charge, say the 5.5 microcoulomb charge. We'll bring that in from infinitely far away and then keep it in its place while we bring in the third charge, the 2.5 microcoulomb charge. So we start with one charge, the negative charge. We bring in the 5.5 microcoulomb charge. Then we hold both of those steady while we bring in the final charge, and we figure out how much work was done to assemble those charges. So please draw your diagram, list all your knowns and unknowns, and recognize that this is an energy situation, and start working on it, please. Okay, we'll start with our negative charge, and we'll call that big Q1, and we'll put it at the origin of our coordinates X and Y. And we'll do this in two parts. We'll start with, we'll call this little q, and what are those equal to? Those charges are equal to 5.5 times 10 to the minus 6 coulombs and negative 6.5 times 10 to the minus 6 coulombs. And initially, it is infinitely far away, and we'll assume that it is not moving. And then we'll bring it in to R final is equal to 0.12 meters, or 12 centimeters. And V final is equal to 0. So we brought this charge in from infinitely far away. It was initially at rest, and we bring it in until it is at rest again at a distance of 12 centimeters away from this charge. So let's calculate the work done to do that, just that part. So once again, this is energy, and the work non-conservative is kinetic energy final minus kinetic energy initial plus potential energy final minus potential energy initial. Everything is at rest to begin with and at the end, so kinetic energy final and kinetic energy initial are both 0. The potential energy of this charge initially is 0 because it is infinitely far away from the other charge. So U initial is 0, and we have work non-conservative is equal to UE final, or work non-conservative is equal to Q times K times Q1 over R final, or the non-conservative work, is equal to 5.5 times 10 to the minus 6 times 8.99 times 10 to the 9 for K times negative 6.5 times 10 to the minus 6 over R final of 0.12, or the non-conservative work is 5.5 times 10 to the minus 6 times 8.99 times 10 to the 9 times negative 6.5 times 10 to the minus 6 divided by 0.12, and we get negative 2.68 joules of work necessary to bring that charge in. Now, what does it mean that the work is negative? It means that we don't actually have to give energy to this charge to get it to move from here to here. It is actually attracted to this charge, so we can actually to move the charge from here to here and have it come to rest again. We actually have to take away energy to get the charge to stop right here. And we have to take away 2.68 joules of energy to get the charge to move from here at rest to here at rest, because this positive charge is attracted to this negative charge. If we didn't take that energy away, then the charge would have a positive amount of kinetic energy right here, and it would still be moving towards this charge. So that's our first step. To get this charge from infinity to here at rest, we had to do a negative amount of work, negative 2.68 joules. Now that this charge is here at rest, and this charge is at rest, we're going to bring in the third charge, and this becomes big Q sub 2 now. And big Q sub 2 is 5.5 times 10 to the minus 6 coulombs. So this charge and this charge are now creating the potential that our third charge feels. And so that is now our Q. I'm going to call that Q, little q2. And that is 2.5 times 10 to the minus 6 coulombs. It is initially infinitely far away from the other charges, and it is initially at rest. And we bring it in to here, where V final is equal to 0 again. So it's at rest to begin with, at rest here. And now we're going to have two charges that are creating the potential. So we're going to have two separate distances. R1 final, or the separation between these two charges, is equal to 0.16 meters. That was given. The separation from here to here, finally, is 16 centimeters or 0.16 meters. the separation between these two charges, R2 final, we're going to have to calculate. It's going to be the hypotenuse of this right triangle, so it's going to be equal to the square root of 0.12 squared plus 0.16 squared. So R2 final is equal to the square root of 0.12 squared plus 0.16 squared, and that is equal to 0.2 meters or 20 centimeters. Okay, so now we know everything we need to use our energy equation again. And that is work non-conservative is equal to kinetic energy final minus kinetic energy initial plus potential energy final minus potential energy initial. And the charge is everything is at rest to begin with, everything is at rest finally. So both of these terms are 0. And we are only working with the potential energy of this charge now. And so it is infinitely far away from both charges to begin with. So U initial is 0. So the work non-conservative is just simply equal to the final potential energy of this charge. Or the work non-conservative is equal to little q2. That's the charge that we're moving, times K times big Q1 over R1 final. So this is the potential energy from Q1, and then we're going to have a similar term with Q2. Big Q2, that is. So we have little q2 again, and then we have K, and then we have big Q2 divided by R2 final. So both Q1 and Q2 are contributing to the potential energy of little q2, or the third charge that we're bringing in. But we have the same form of the potential energy in both cases. Little q2 times K times big Q over R, and the only thing that changes is that the subscript for big Q and the subscript for R change. So we have little q2 K, big Q2 over R2 final. And we just have to calculate, we have to put in our numbers and calculate that. Work non-conservative is little q2, which is 2.5 times 10 to the minus 6 times K, which is 8.99 times 10 to the 9 times big Q1, which is negative 6.5 times 10 to the minus 6, all divided by R1 final, which is 0.16, and then plus 2.5 times 10 to the minus 6 times 8.99 times 10 to the 9 times big Q2, which is 5.5 times 10 to the minus 6, all divided by R2 final, which was 0.2. So the work needed to bring in the third charge is, 2.5 times 10 to the minus 6 times 8.99 times 10 to the 9 times negative 6.5 times 10 to the negative 6 divided by 0.16 plus 2.5 times 10 to the negative 6 times 8.99 times 10 to the 9 times 5.5 times 10 to the negative 6 divided by 0.2, and I get negative 0.295 joules. So once again, in order to get this charge to be at rest here and at rest here, we had to take away some energy from it. We had to do negative work on it. We had to take away 0.295 joules. Okay. So, if we want to know the total work total would be equal to negative 2.68 minus 0.295. So the total work is negative 2.68 minus 0.295. And so I get negative 2.98 joules. So the total energy required to bring these three charges to their final positions at rest was negative 2.98 joules, meaning we had to actually take away energy from them to get them to be at rest in this position. If we didn't, then they would have kinetic energy and they would be moving towards each other. And that answers the question that we were asked. So far in our discussion of field forces, we've talked about the electric force and the electric field. The electric charge feels the electric force, and the electric charge is also the source of the electric field. Similarly, mass feels a force from the gravitational field, and mass is the source of the gravitational field. Let's talk about magnetic fields now. What is it that feels a force from the magnetic field? It is a moving charge. So the source of the magnetic field is also a moving charge. And moving charges we are going to call an electrical current. The expression for the magnetic field created by a long straight current is B vector is equal to mu naught, or mu sub 0, which is a constant. It has a value of 1.257 times 10 to the minus 6 in basic metric units, which would be Teslas times meters divided by amperes. So the magnetic field is mu naught times I, the amount of current that we have, divided by 2 pi r. So the magnetic field decreases the farther you get from a current as 1 over r, 1 over the distance. So the magnitude of the magnetic field is mu naught I over 2 pi r, and the direction of the magnetic field is the right-hand direction. So just as we had a right-hand rule for magnetic force, we also have a right-hand rule for the direction of the magnetic field. And the right-hand rule, you can see in this diagram, is that if you place your right thumb in the direction of a current I, then the magnetic field circles around the wire, or circles around the current in the direction of your right fingers. So in that diagram, the thumb is pointed upwards along the wire, and the right fingers circle counterclockwise around the wire, and the magnetic field does the same. The magnetic field lines circle counterclockwise around the wire. So, the electric field diverges from positive charges and converges on negative charges. The magnetic field doesn't diverge from anything. Instead, it circles around electric currents. And it circles around the electric currents in the sense of your right hand's fingers circling around your right thumb. So once again, the magnetic field due to a current is equal to mu naught I over 2 pi r, and it's in the right hand direction. Let us work out an example to make that a little more concrete for you. A long straight wire carries a current of 50 amperes. An electron traveling at 1.0 times 10 to the 7 meters per second is 5 centimeters from the wire. What force, magnitude and direction, acts on the electron if the electron's velocity is directed toward the wire? And here's a diagram for you so you can see the situation that's being described. So there's two things that you have to do here. The first is to figure out the magnitude and direction of the magnetic field at the position of the electron at this moment, and then figure out the force on the electron. So draw your diagram, list all of your knowns and unknowns, and answer that question, please. Okay, here is our wire. I is equal to 50 amperes, and we're given our x and our y coordinates. Our electron, and it's an electron, so Q is equal to minus E, which would be negative 1.6 times 10 to the minus 19 coulombs, and it is moving towards the wire with a speed of 1 times 10 to the 7 meters per second, and it is at a distance r of 5 centimeters, which would be 0.05 meters. And I do believe that that is our diagram and everything that we're given. And the question is, what is the magnetic force? What is the magnetic force on the electron? Okay, well, we know that the magnetic force is equal to Q times V times B in the right hand direction. And so we know Q is negative 1.6 times 10 to the minus 19 coulombs. V is 1.0 times 10 to the 7 meters per second. B we don't know now. We're not given B, so we're going to have to figure out what B is. So I'm actually just going to stop this right here and move on to figure out what B is. Okay. B is equal to, we were just told, mu naught I over 2 pi r in the right hand direction. Okay, so we know mu naught is 1.257 times 10 to the minus 6. I is 50 amperes and over 2 pi times r, and r is 0.05. So we've got everything we need here to calculate the magnitude of B. What is the right-hand direction? Okay, well, I'll have to take my thumb and point my thumb in the direction of the wire, and we'll see that my fingers curl in this sense. So if you imagine putting my hand around the wire, the magnetic field, my fingers in the magnetic field are going to curl out on this side, loop over, and curl in on this side. Actually, I'll turn that, and you can see it this way. Here's my thumb along the wire, and my fingers are pointing into the page in the place where the electron is. So the magnetic field line goes into the page on this side, and then curls around and comes out of the page on the top of the wire. So B is out of the page on this side of the, whoops. Actually, I'm sorry, B is not out of the page. B is into the page. Do it again. There's my thumb. My fingers are going into the page. So B itself is into the page over here, and then it curls around and comes out of the page up here. So once again, there's my thumb. My fingers curl out of the page over here, and out of the page above the wire, and into the page below the wire. So B is into the page, which I'm indicating with a cross. And so the direction is in to the page. We'll just write in. Okay, so what is the magnetic field? 1.257 times 10 to the minus 6 times 50 divided by, parentheses, 2 times pi times 0.05, and that is 2.00 times 10 to the minus 4 Tesla into the page. Okay, so this number right here is what we need for B right here. 2.00 times 10 to the minus 4. And now, what is the right-hand direction? Okay, well, that's where we use our other right-hand direction. And my thumb is pointing in the direction of V. My fingers are pointing in the direction of the magnetic field. And so the right-hand direction is in the negative X direction. Okay, so thumb in the direction of V, fingers in the direction of the field. So the right-hand direction is going to be the negative X direction. I'm just going to write negative X for my direction. So FB is negative 1.6 times 10, negative 1.6 times 10 to the negative 19 times 1 times 10 to the 7 times 2 times 10 to the negative 4, and that is going to give me 3.20 or negative 3.20 times 10 to the negative 16 in the negative x direction. Now I have two negatives, so the magnetic force is 3.20 times 10 to the negative 16 newtons in the positive x direction. So the force on the electron is going to be 3.2 times 10 to the minus 16 newtons in the positive x direction, because here we have a double negative. We have negative and negative. And that answers the question that we were asked. Let's have one more question. A rectangular loop of wire carrying a current I1 is equal to 2 milliamperes is next to a very long wire carrying a current I2 is equal to 8 amperes. The magnetic force on the two sides of the loop cancel out, but the magnetic forces on the top and the bottom don't. So what I would like you to do is to calculate the total magnetic force on the rectangular loop due to the long wire's magnetic field. And here's a diagram of the situation. Now I would like you to draw your own diagram, calculate the magnetic field that the 8 ampere wire creates, and then calculate the force on the top and the bottom of the rectangular loop. Okay, here's our diagram. I2 is equal to 8 amperes. And here's our rectangular loop, and it is carrying current in this sense. I1 is equal to 2 milliamperes, or 2 times 10 to the 2 times 10 to the negative 3 amperes. This side is 2 centimeters. We'll call that R1, is 0.02 meters away from this wire, whereas the top wire is R, we'll call it R2, is an additional 5 centimeters away. So this side is 5 centimeters, so the total distance is 7 centimeters. So R2 is 0.07 meters. So this wire is 2 centimeters from the long straight wire, and this top side is 7 centimeters, or 0.07 meters away from the bottom wire. Okay, first, let's figure out the direction of the magnetic field created by the long straight wire. Once again, if I stick my thumb, let me rotate the page. If I stick my thumb in the direction of the current, then the magnetic field is going into the page on this side and coming out of the page on this side of the wire. So on top of the wire, we'll call that B. B is out of the page. So the magnetic field is out of the page everywhere up here. Consistent with my right-hand rule, my fingers are going to curl out of the page on this side. So that is going to exert a force. This magnetic field created by this long straight wire is going to exert a force on this wire and it's going to be in the right-hand direction for the force. And the right-hand direction for the force is that we stick our thumb in the direction of the current and our fingers in the direction of the magnetic field. And so let's see what the direction of the force is on the short wires. Let's start with the bottom. On the bottom of the loop, the magnetic field is out of the page, just like my fingers are pointing, and my thumb is to the left. So the force on the bottom of the wire, call it F1, is up. The force on the left side of the wire is to the right. The force on the top of the wire, okay, my thumb is in the direction of the current for the top of the wire. My fingers are out of the page. So the force on the top of the wire, we'll call that F2, is down. And the force, oops, this is not drawn right. There we go. We have to circulate around like this. The force on this side of the wire is to the left. So we have a force right and left, which are canceling each other out, the question said. But F1 and F2, while in opposite directions, don't cancel each other out. And the reason is because the magnetic field at this position is stronger than the magnetic field at this position because we are closer to the wire creating the magnetic field here than we are here. So what is the magnetic field of this wire? B is equal to mu naught I2 over 2 pi r. That's the magnitude of the magnetic field. And so for R1, which is smaller than R2, having a smaller number in the denominator will give us a bigger magnetic field. So F1, we're just going to do the magnitude now. F1 is B times I times the length of this wire, and the length of that wire, we're told, is 9 centimeters, 0.09 meters. I forgot to put that in. B times I times L, which is, and that should be I1. So that would be mu naught I2 over 2 pi times R1 times I1 times L. That's the force on wire 1. And the force on the top side, F2, is going to be B I1 times L. So F2 is mu naught I2 over 2 pi R2, the distance of the top wire from the long straight wire, times I1 times L. So the only difference is in this distance in the denominator, in R1 and R2. Everything else is the same. So let's calculate that. F1 is mu naught 1.26 times 10 to the minus 6 times I2, which is 8, over 2 pi times R1, which is 0.02, times I1, which is 2 times 10 to the minus 3, times L, which is 0.09. So the force on the bottom of the wire is 1.26 times 10 to the minus 6 times 8 times 2 times 10 to the minus 3 times 0.09 divided by, parentheses, 2 times pi times 0.02. And that gives us a force of 1.44 times 10 to the minus 8 newtons, and it's going to be upwards. And what is F2? F2 similarly is 1.26 times 10 to the minus 6 times 8 times 2 times 10 to the minus 3 times 0.09 divided by 2 pi times 0.07. So the only thing that has changed is the distance of this wire from this wire as opposed to this wire. And that gives us F2. Everything is the same. All I have to do is change the denominator from 0.02 to 0.07, and that gives me a force of 4.13 times 10 to the minus 9 newtons. So we have an upward force on the bottom wire of 1.44 times 10 to the minus 8 newtons and a downward force of 4.13 times 10 to the minus 9 newtons. So the total force is going to be, we'll call that our y direction. We'll make that y. So force total y is 1.44 times 10 to the minus 8 minus 4.13 times 10 to the minus 9. And the total force in the y direction is 1.44 times 1.44 times 10 to the minus 8 minus 4.13 times 10 to the minus 9 gives me 1.03 times 10 to the minus 8 newtons. So the net force on the loop of wire is 1.3 times 10 to the minus 8 newtons away from the long straight wire. And that answers the question we were asked. Next time, we're going to talk some more about currents as the source of magnetic fields. Until then, think physics.